In the deep dark, some objects speak without light, without fire, and without spectacle. A neutron star is one of them. It is a city-sized sphere where matter stacks into layers, where gravity bends paths, and where time itself can appear in steady pulses. In this documentary arc, signals become a quiet language. A fading surface glow hints at hidden interiors. A rising chirp reveals tidal softness and stiffness. A brief post-merger remnant shows how close nature comes to collapse, and how it sometimes lingers at the edge. Space Dream's documentary begins here with calm checkpoints across extreme density magnetism and the slow, readable patterns that remain. A neutron star sits in space as a small object with an outsized consequence. The simple truth is that immense mass fits into a sphere only about 20 kilometers across, close to the span of a large city. In that region, darkness holds a compact globe whose edge looks clean and sharp. The surface is not a vague boundary. It is a real crust with a thinness that feels surprising beside the weight beneath it. A slow image forms of a smooth dark sphere ringed by a faint halo where light paths curve. The first understanding arrives early. Extreme density is not a poetic phrase here. It is a physical condition where familiar materials stop behaving like materials. The mind tries to picture compression by imagining pressure on foam or clay. That approach fails quickly. The scale jump is too steep. A whole star's core ends as a compact remnant. It rests in silence, yet it carries gravity strong enough to reshape the space close to it. In that closeness, motion and time keep their usual meanings, but their ratios shift. A second image drifts in still and concrete. A thin crust sits over deeper layers like a brittle glaze over a depth that never yields. Tiny height changes on the surface map into steep changes in gravity. Shadows near the limb look darker and more decisive. Gradients sharpen over short distances. The boundary between near and far becomes abrupt, as if distance itself has become thicker. The first core idea takes shape in plain language. Density means mass packed into less room. On a neutron star, the packing becomes so extreme that atoms do not keep their ordinary spacing. The empty space that makes everyday matter gentle and springy is squeezed away. A calm analogy arrives without drama. It resembles a storm cloud pressed into a single raindrop, where the same substance occupies far less volume. The value of this analogy is limited, yet it points to the right direction. Compression does not merely shrink, it changes what can exist. The payoff lands softly. If matter is pressed enough, the usual rules of chemistry fade. In their place, deeper rules of particles and pressure hold the shape together. A third image becomes the main scene for this section. A small sphere turns slowly in darkness. Its surface looks smooth at first. Then subtle bands appear. A faint brightening near one side hints at light bending along curved paths. The sphere's edge is not an exact circle in the way a simple drawing suggests. It is a boundary seen through distorted geometry. Light behaves as if space near the surface has a slope. Rays that would have missed the object can be pulled into tighter arcs. The result is a quiet paradox. More of the surface can be visible than a flat intuition expects, even without any beam or lamp nearby. The next understanding slips into place. A neutron star is not supported by heat, or by ordinary gas pressure. It is supported by a kind of stiffness that comes from the rules of matter itself. A name exists for this idea, yet the idea is simpler than the name. Degeneracy pressure is resistance from crowded particles obeying quantum rules. A short definition sits, and then relaxes. In crowded matter, particles cannot all share the same state. In a gentler comparison, it resembles a packed theatre, where no two bodies can occupy the same seat. The important part is not the theatre. The important part is the limit. When matter is forced into extreme closeness, a new kind of pressure appears that does not depend on warmth. The payoff arrives as a clean statement. The star can cool greatly and still remain held up because this stiffness comes from structure, not from heat. The scene returns to the crust. The outermost layer can be imagined as a rigid shell. Its thickness is tiny beside the star's radius. Beneath it, matter becomes a dense mixture where nuclei crowd together and electrons move in a strange, highly compressed sea. Deeper still, the identity of matter shifts again. The story does not require a long list of layers to feel the change. One clear physical detail is enough. The pressure rises so steeply with depth that a small step downward leads to a dramatically different environment. A gradient that would take mountains on a planet happens over a short distance here. The scale shift is gentle and steady. From a surface that looks like a smooth stone, the view moves inward to a region where the idea of a stone becomes meaningless. The object remains small in size, yet it contains a deep interior that is more like a whole world of pressure stacked into a narrow span. Another image settles, slow and vivid. A thin, pale crust floats above a dark interior like ice over a deep ocean, yet the ocean is not liquid water, and the ice is not made of familiar crystals. The mind searches for a texture. It finds something like hard candy under a heavy press. It looks glossy and unyielding, but a hidden brittleness lies within. When stress changes, the crust can shift or fracture. That fact matters later, but it does not need a sharp emphasis now. The section's second concept appears and then stays contained. Neutron matter is matter dominated by neutrons in close contact. The short definition does not try to draw a complete picture, it only marks a boundary. In ordinary life, protons and electrons keep atoms balanced. Here gravity pushes so hard that electrons are squeezed into protons in the deepest regions. Neutrons become the main residents. The analogy that fits best remains quiet. It resembles a crowd that loses its individual spacing until only the presence of bodies remains. The payoff arrives as a small unlock. This is why the object earns its name. It is not only a small star, it is a new state of matter stabilized by gravity and quantum rules together. A limit of intuition appears and it is stated plainly. The interior cannot be seen directly. The exact behavior of matter at the deepest densities is not pinned down by simple observation. Only indirect clues exist, such as mass and radius relationships, and the way the star's gravity affects nearby light and motion. Those clues constrain possibilities, but they do not select one single answer. The limit is a limit of inference. Many models can fit the same outward facts. Uncertainty remains even when the exterior is described well. The result is not confusion. It is a clear boundary line around what is known. Another visual anchor arrives to keep the rhythm slow. The neutron star rests against a background of sparse dust and faint starlight. Near it, light paths curve in subtle arcs. A thin crescent of brightness forms where a grazing ray is pulled around the limb. The edge looks like a tight outline inked onto darkness. The object feels like a small coin, yet its gravity suggests a far larger presence. The final unlock of this opening section settles in quietly. Neutron stars turn the universe into a laboratory of extremes without requiring any human stage. Their size is modest, their mass is heavy. Their physics sits at the border between what intuition handles and what only careful reasoning can hold. The scene softens toward what follows. Collapse and formation provide the next step in this arc. The calm sphere remains in view for a moment longer, then the attention drifts backward in time toward the moment when a massive star's core loses its balance and begins to fall inward. A massive star ends its long balance with a quiet change in its center. The core stops making enough outward pressure so gravity begins to win, and the collapse starts. In that region, the outer layers still look bright and spacious. The center becomes a dim well that deepens by the moment. A slow visual anchor settles on nested shells like soft layers folding inward in silence. The first understanding arrives early. A neutron star begins as a normal core that loses its support and falls into itself. The idea sounds simple. The details become strange only because the scale is enormous. The heart of the star shrinks while keeping its mass. The inward motion gathers speed. Heat rises, yet heat is not the main support any longer. A calm analogy carries the sense of inevitability. It resembles a tall stack of dry sand that holds for a long time. Then one grain shifts and the stack settles into a tighter mound. The mound is smaller, yet it holds the same sand. The payoff lands gently. Collapse is not a blast from the outside, it is a reorganization from within. The star's center passes a threshold where old balances no longer work. The section keeps two core concepts in view. The first is gravitational collapse, which is inward falling when pressure cannot resist. The second is conservation of angular momentum, which keeps spin linked to size. These ideas stay close to plain language. No long chain of terms is needed. The scene continues through a slow inward drift. Layers that once sit far apart begin to slide closer. Boundaries blur as density rises. Gradients steepen. A small inward step now changes conditions sharply. The outer star can still spread across an immense distance. The core contracts to a compact region. A scale shift happens without force. It moves from the size of a star to the size of a small world. The second visual moment arrives as a clear checkpoint. A dark center tightens while the brighter gas above it hesitates, then follows. The motion looks like a slow whirlpool in a cloud, but without water and without sound. As the core shrinks, its rotation speeds up. Conservation of angular momentum means a rotating object spins faster when it becomes smaller. The definition stays short. Angular momentum is rotation that stays the same unless something removes it. The analogy is quiet and distinct. It resembles a long ribbon wound loosely on a spool. When the ribbon is wound onto a smaller spool, the turns become faster. The payoff settles in. Spin is not added, it is concentrated. A later neutron star can rotate rapidly, because the core contracts not because anything pushes it. The physical details sharpen. The core becomes a dense sphere with a steep pressure gradient. The surface of that future sphere does not exist yet, but the boundary begins to form. A sudden change in density appears where matter becomes hard to compress. The inward rush meets a kind of resistance, and the collapse changes character. The outer layers respond. Some material falls inward. Some material can rebound outward in complex flows. This remains a broad description. It avoids sharp drama. It focuses on structure. Motion divides into regions. In one region, matter plunges. In another, matter lingers and curls. The third visual anchor arrives calm and slow. A spherical wave of compression travels inward like a dark front. Behind it, matter is denser and less transparent. Ahead of it, matter is still familiar plasma. The boundary between them is a moving surface. It is not a wall. It is a gradient that steepens as the core tightens. The next understanding becomes clear. The path to a neutron star is a process of thresholds. Each threshold reduces the range of possible states. Pressure sources that once matter stop mattering. New ones take over. The section's single number appears and stays gentle. The core's final compact remnant can be about 20 kilometers across, like the span of a large city. The comparison keeps the scale grounded. The change is not only in size, it is in time. The collapse happens quickly compared with the long life before it. Yet the remnant can persist for ages. A scale shift stretches from moments to cosmic durations. A quiet limit of observation arrives and is stated plainly. The deepest part of the collapse is hidden behind thick, opaque layers. Direct sight cannot track the exact interior sequence. Only indirect traces can constrain the timing and the final outcome. Models can agree on the broad steps and still disagree on details. The limit is a limit of resolution in inference. The interior is too dense and too brief to be fully reconstructed from afar. That boundary does not weaken the story. It gives it shape. The scene returns to the nested shells as the main visual anchor. The star's outer volume remains vast. The center becomes a compact kernel. The contrast between the two sizes becomes almost gentle when seen from far away. A slow, steady inward motion replaces any sense of spectacle. The payoff settles as a final clarification. A neutron star is not a separate kind of object formed from scratch. It is an ending shaped by gravity pressure and conserved rotation. The section closes with a soft forward motion. The next step follows the matter as it becomes neutron-rich and changes identity. The inward journey continues toward the moment when electrons and protons can no longer remain separate. Somewhere inside the collapsing core, ordinary atoms quietly stop being stable. The key change is that electrons and protons merge into neutrons, so matter becomes far more compact. In that region, the pressure rises so sharply that distance feels different. A small inward drift crosses a boundary and the rules shift. The main visual anchor forms as a dim sphere wrapped in concentric layers. Each layer looks slightly darker than the last. The gradient is smooth at first, then it steepens. The first understanding settles early. A neutron star is born when the core becomes neutron-rich and can compress much further than normal matter. The reason is not a special chemical reaction. It is a change in what particles can exist under crushing conditions. The section keeps to three ideas. Electron capture changes protons into neutrons. Neutronization is the growing dominance of neutrons in dense matter. Degeneracy pressure is stiffness from crowded particles obeying quantum rules. The last term stays brief and then returns to plain language. Electron capture is when an electron joins a proton and makes a neutron. In a quiet analogy, it resembles a crowded hallway where one kind of traveller steps into another space and the count changes. The matter looks almost the same from far away, yet its internal bookkeeping shifts. The payoff arrives as a clean unlock. Gravity wins more easily when electrons vanish into neutrons, because the material loses a key source of resistance. The scene returns to the layered sphere. At the outskirts of the core, electrons still move in a compressed sea. Deeper in, they begin to disappear into protons. The physical detail is a boundary that moves. It is not a sharp wall, but it is a real front. Ahead of it, matter remains more familiar. Behind it, matter becomes more neutron-rich and more tightly packed. The change is not gradual everywhere. It accelerates as density climbs. A second visual moment appears to keep the rhythm slow. A darkened shell thickens like a stain spreading through wood grain. The stain is not a liquid. It is a change of composition. It spreads inward and outward in response to pressure gradients. The next understanding arrives with calm certainty. Neutrons allow matter to pack into a denser state because they carry no electric charge. Protons repel each other through electric force. Electrons provide balance and structure. When electrons merge into protons, that balance shifts. A new kind of crowd forms where neutrality makes close packing easier. The analogy remains distinct. It resembles removing the air from a bag of loose flour. The bag becomes smaller without adding anything new. The flour was always there, but empty space is reduced. The payoff lands softly. The core can shrink further because a major form of internal spacing disappears. The section's single number appears and stays grounded. At birth, the core can contain about 1 to 2 solar masses within a compact remnant, like fitting the weight of a bright star into a sphere the size of a city. The comparison carries the scale without strain. The size and mass contrast becomes the point. A small object holds a star's worth of gravity. A gentle scale shift follows. The collapse that unfolds over moments sets the stage for a remnant that can persist for billions of years. The scene holds on a close view of the interior. The layers are imagined as bands of density, not as coloured stripes. Near the centre, matter becomes so compressed that intuition about solids and liquids weakens. The concept of a single atom becomes less useful. The pressure is not a sensation. It is a condition that sets what particles can exist. Another visual anchor arrives to maintain the cadence. A thin, bright rim outlines the core where density changes quickly. It resembles the edge of a shadow cast in mist. The edge is sharp because the gradient is steep. This sharpness matters. It marks a region where small changes in depth cause large changes in behaviour. The next unlock appears gently. Degeneracy pressure becomes crucial because it does not rely on temperature. The remnant can cool and still resist further collapse. This is the simplest reason a neutron star can endure. Heat can fade, the quantum stiffness remains. The section includes a limit of intuition and states it plainly. The exact sequence of neutronization cannot be watched directly because the core is opaque and short-lived. Only indirect evidence exists through the final mass radius and the behavior of the remnant afterward. Models can differ in the details and still agree on the outcome. The limit is a limit of direct measurement and a limit of inference resolution. The interior changes happen behind dense layers that block clear signals. That boundary does not erase knowledge. It simply marks where certainty becomes a range. The main visual anchor returns for a final slow pass. The layered sphere settles into a more stable form. The moving boundary of composition slows and becomes part of the structure. The gradients remain steep. The object becomes small, dense, and quietly persistent. The payoff arrives as a final clarification. Neutrons are not added as a decoration. They are the consequence of gravity pushing matter past a familiar arrangement. The section closes with a soft transition. Rotation and magnetism begin to matter more once the compact remnant exists. The next step follows how spin and fields take a shrunken core and give it a distinctive rhythm. A neutron star's surface looks simple until light begins to misbehave near it. The key idea is that strong gravity bends light and shifts its colour, so the surface is seen through a quiet distortion. At this distance, the star appears as a dark bead with a crisp edge. Closer in, the edge becomes less certain. The main visual anchor settles on a smooth sphere above a thin haze of scattered dust. A faint arc of brightness clings to the limb. It resembles a soft ring that never closes. The first understanding arrives early. Gravity does not only pull matter, it also curves the paths that light prefers to follow. The mind often imagines light as straight lines. Near a neutron star, straightness becomes an approximation that works only far away. The section holds to three concepts. Gravitational lensing is light bending through curved space near mass. Gravitational redshift is light losing energy while climbing out of gravity. Escape speed is how fast something must move to leave. The first two ideas stay in the foreground. The third remains a supporting shadow. Gravitational redshift is light shifting to lower energy when escaping gravity. The analogy stays gentle and distinct. It resembles a clear bell tone that deepens as it drifts upward through thick air. The tone is not changed by distance alone. It is changed by the effort of leaving a deep region. The payoff arrives as a calm unlock. The surface can glow at one colour, yet the far view receives a slightly softer version. The colour is not painted over, it is transformed by the climb. The visual anchor returns to the limb. Light behaves as if the star's boundary is wrapped in curved glass. Rays that begin at an angle can be guided around the sphere. Some can skim along and then depart. The result is a subtle physical detail. The star can reveal more of its surface than a simple sphere would, because bent paths let hidden regions contribute. The edge becomes a place where geometry shows itself. A second visual moment appears to keep the rhythm even. The sphere turns slowly. A shallow shadow band lies across it. The band is not cast by any object. It is the consequence of brightness changing with angle and path. The gradient is steep near the limb. It softens toward the centre. The next understanding settles in. Lensing is not a magnifying trick alone. It is a rearrangement of angles. A surface point can be seen along a path that is not expected. This means a hot region can appear closer to the edge than it really is. It also means size estimates can be slippery. The analogy stays grounded. It resembles looking at a pebble through rippling water. The pebble stays where it is, yet its outline shifts. The payoff lands gently. Apparent shape and true shape can diverge even when the object is steady. The section's single number appears and stays simple. The escape speed near the surface can be about half the speed of light, like a thrown stone that would need to leave faster than any ordinary launch. The comparison keeps it every day without using machinery. The meaning is clear. Gravity is so deep that leaving requires a speed near an ultimate limit. This also connects to time. Processes at the surface still happen in local seconds. Yet the far view can receive them with a slightly different rhythm, because deep gravity affects rates. The scale shift is soft. It moves from a short flicker at the surface to a long, quiet observation from far away. The main visual anchor deepens. The faint arc at the limb becomes more pronounced as the viewpoint shifts. It is not a complete ring. It is a crescent of guided light hanging like a thin glaze on darkness. The surface looks both near and far at once. The eye wants to decide. It cannot. The next understanding arrives as a small unlock. Measuring the star's radius from its glow is harder than it sounds. The glow is altered by redshift. The apparent area is altered by lensing. Even the surface temperature inferred from colour is nudged. None of this hides the star completely. It simply means every measurement is a puzzle of geometry and gravity combined. A limit of observation appears and is stated plainly. The surface cannot be visited or directly sampled. The only information comes through light that has been bent and shifted. Different models of the atmosphere and surface emission can fit the same distant signal. The limit is a limit of inference and of spectral resolution. Without a perfectly known surface pattern, multiple combinations of size and temperature can match. Uncertainty remains as a range, not as a void. A third visual moment arrives with calm clarity. A thin mist of particles surrounds the star, sparse and cold. Light grazing the limb scatters slightly. The scattered glow is faint, yet it reveals the curvature of paths. The boundary becomes a place where brightness is folded into itself. The payoff lands softly. Even without motion or pulses, a neutron star announces its gravity through how light leaves it. The section closes with a gentle forward drift. Once rotation becomes faster, these same distortions shape the way signals rise and fall. The next step follows how spin and magnetic geometry create repeating beams that can be timed with quiet precision. A neutron star can turn so steadily that its rotation becomes a kind of quiet signature. The key reason is conservation of angular momentum, so shrinking size concentrates spin into a fast and stable rhythm. In that region, darkness holds a compact sphere and the space around it seems to circle. The main visual anchor settles on a faint belt of drifting particles around the star. The belt is thin and uneven. It forms a flat disk that glows only slightly from gentle heating and friction. The first understanding arrives early. Rotation is not added during collapse. It is preserved and sharpened. The core begins as a slowly rotating region inside a larger star. As the core contracts, the same rotational tendency becomes faster because the radius becomes smaller. A calm analogy supports the idea without any performer. It resembles a wide river entering a narrow canyon. The flow does not gain new water. The same water speeds up because the channel tightens. The payoff lands softly. A neutron star can spin rapidly because the pathway for rotation narrows, not because any external push occurs. The section holds to three concepts. Angular momentum connects rotation to size and stays conserved when little escapes. Moment of inertia is how mass distribution affects ease of spinning. Equatorial bulge is a slight widening from rotation. The second and third stay gentle and visual. The main focus remains the link between shrinking and speeding. The compact sphere turns. The faint disk around it shows the turn as a slow gradient. The inner edge of the disk orbits faster than the outer edge. A physical detail appears as a boundary. The disk has a sharp inner rim, where material cannot orbit stably any closer. The rim looks like a thin ring with a clean edge darker inside and brighter just outside. The next understanding settles in. Rotation is not perfectly uniform in all layers. The crust can behave like a rigid shell. The deeper interior can shift in subtle ways. Yet the whole object maintains a remarkably steady overall spin. The steadiness matters because it allows patterns to repeat with little drift. A second visual moment arrives as a checkpoint. A shallow bulge appears at the equator, a slight flattening at the poles. The shape remains close to spherical, but not perfectly. The gradient of gravity changes with latitude. The surface becomes a map of tiny differences. The payoff lands as a small unlock. Fast rotation leaves a geometric imprint. The star's shape and gravity field carry faint signatures of spin even when no glow changes are present. The single number appears and stays simple. Some neutron stars rotate about once every second like a slow metronome beat continuing in darkness. The comparison keeps it grounded and calm. Many rotate faster, but the section does not chase extremes. One steady beat is enough to hold the idea. The scale shift follows gently. A second becomes a repeating unit that can persist for millions of years. A short rhythm can outlast entire eras of surrounding change. The disk remains the main anchor. Particles drift in a thin plane. Their paths are nearly circular. The inner rim looks like a fine ring of frost seen from afar, though it is not frost and not cold in the usual sense. The ring is simply a boundary where motion reorganizes. Light behaves as if the ring brightens when turbulence increases then settles again. The next understanding becomes clear. Rotation can slowly change over time. The star can lose energy through radiation and outflows, but the change is gradual. This means the spin rate can be measured as a slow drift rather than a sudden fall. The analogy stays distinct. It resembles a spinning top on a smooth floor that loses speed so slowly that the change is noticed only by patient comparison. The payoff arrives softly. A tiny change in spin rate can reveal hidden processes in the star's magnetic environment and interior coupling. A limit of observation appears and is stated plainly. The internal distribution of mass cannot be seen directly, so moment of inertia is inferred indirectly. The inferred value depends on models of the star's radius and the behavior of its exterior fields. The limit is a limit of inference and of degeneracy in models. Different interior structures can produce similar external timing behavior. The observation constrains possibilities, but it rarely selects one unique interior. The visual anchor returns with a slow concrete pass. The disk's inner rim remains sharp. The outer disk fades into a thin haze. The star's equatorial bulge remains subtle. The whole system looks like a small dark kernel with a flat whisper of matter around it. The payoff settles in as a final clarification. Spin is a stored memory of collapse. It is concentrated into a stable beat that can carry information forward through vast time. The section closes with a gentle transition. Once magnetism shapes the space around the spinning star rotation, can turn fields into structured patterns. The next step follows how magnetic geometry rises and how it prepares the conditions for pulses. A neutron star's magnetism stays invisible until it begins shaping the space around it. The key idea is that a strong magnetic field forms structured arcs and channels, guiding charged particles and organizing emission. In that region, the star is a compact sphere with a dark surface and a faint surrounding glow. The main visual anchor settles on two broad loops of field geometry, rising from the surface and curving back. The loops do not shine by themselves. Their presence is suggested by a thin, hazy sheath that follows their shape. The first understanding arrives early. The magnetic field is not a separate object. It is a pattern in space that reaches far beyond the star. It begins in the star's interior and threads through the crust. It extends outward as a structured envelope. A calm analogy holds the shape without borrowing any human scene. It resembles the grain lines in a piece of wood. The wood stays still, yet the grain reveals a hidden order. In the same way, space near the star carries an order that can be traced by how material moves. The payoff lands softly. Magnetism provides a framework. It tells particles where they can travel easily and where they are constrained. The section keeps to three concepts. Magnetic field geometry is the overall shape of field lines in space. Magnetosphere is the region where the field dominates charged motion. Field line curvature is how sharply the geometry bends and where stress concentrates. The terms remain light. The focus stays on shape boundaries and motion. At this distance, the magnetosphere looks like a faintly structured fog. It is not uniform. It is denser along certain arcs. Near the magnetic poles, the fog tightens into narrow funnels. Near the equator, it spreads into broader regions. A physical detail appears as a boundary. There is a surface-like transition where magnetic control fades and other influences take over. It is not a hard wall. It is a gradient where ordered motion becomes less ordered. The second visual moment arrives as a slow checkpoint. A thin band of glow forms above the star's surface. It is brightest near the poles. It fades toward the sides. The band is not a ring. It is a pair of oval caps like two pale patches on a dark sphere. The next understanding settles in. A magnetosphere is not a static haze. It is a place where particles move along curved routes. Charged particles spiral around field lines while also sliding along them. The spiral is small. The path along the line can be long. The scale shift is gentle. A tiny corkscrew motion can be nested inside a journey that stretches far beyond the star's radius. The payoff lands as a quiet unlock. The field turns chaotic motion into guided motion, and guided motion can produce repeatable signals. The single number appears and stays grounded. The magnetosphere can extend thousands of kilometers like a region larger than a small planet wrapped around a city-sized core. The comparison keeps the contrast calm and clear. The star remains compact. The field's influence reaches outward to a much larger volume. Within that volume, geometry matters. Field lines curve more sharply near the surface. Their curvature relaxes farther out. This creates differences in how particles accelerate and where emission concentrates. The main visual anchor deepens. The two broad loops appear as translucent arches. Along them a faint brightness pulses softly. The pulse is not a clock yet. It is a hint of structured motion. Light behaves as if the emission prefers certain corridors. Outside those corridors, the darkness stays clean. The next understanding arrives as another unlock. The shape of the field can change slowly over time. Stresses in the crust and in the magnetosphere can twist the geometry. A twisted geometry stores energy in the shape itself. This does not require a violent scene. It is a quiet accumulation of tension in curvature and alignment. The analogy remains distinct and gentle. It resembles a garden hose that is slightly kinked. Water still flows, yet the kink stores a tendency to shift. In the same way, a twisted field stores a tendency to rearrange. The payoff lands softly. Field geometry is not only a map. It is a reservoir of structure that can influence when and where energy is released. A limit of observation appears and is stated plainly. The field lines cannot be seen directly. Only the radiation and particle behavior reveal their arrangement. Different magnetic geometries can produce similar outward signals, especially when viewed from far away. The limit is a limit of inference and of geometric ambiguity. Without knowing the exact angle between spin and field, multiple models can fit the same pattern. This boundary does not erase understanding. It shapes it into ranges and families of possibilities. The third visual moment arrives to keep the cadence slow. A faint sheet of particles drifts along an equatorial region. Above it, arches of magnetism rise and return. The brightness is soft and uneven. It looks like a thin auroral veil, but without any sky and without any planet. The physical detail is a sharp gradient at the edge of the emitting region. Inside, the edge motion is guided and bright. Outside, its motion is freer and dim. The final unlock settles in quietly. Magnetism turns a compact star into a structured environment. It sets up corridors, caps, and boundaries that can repeat and evolve. The section closes with a gentle transition. Rotation will soon sweep this geometry through space. When an emitting corridor crosses a distant line of sight, a pulse can appear. The next step follows how that repeating sweep becomes the signature of a pulsar. A pulsar feels like a repeating whisper that returns with patient regularity. The key reason is that a narrow beam of emission sweeps through space as the star rotates, and the beam is seen only when it crosses a line of sight. In that region, the neutron star remains a dark sphere. Around it, the magnetosphere forms curved corridors and open funnels near the poles. The main visual anchor settles on a thin cone of faint glow, rising from one magnetic pole. The cone is narrow at the surface. It widens gradually as it extends outward like a soft brushstroke drawn into emptiness. The first understanding arrives early. Pulses are not bursts that start and stop at the star. They're a viewing effect created by geometry and rotation. The star emits in preferred directions. Rotation makes those directions sweep. When the sweep aligns, a pulse appears. When it does not, the space stays quiet. The section keeps to 3 concepts. Beam geometry is the directional shape of emission in the magnetosphere. Magnetic axis tilt is the offset between the magnetic poles and the rotation axis. Pulse period is the repeat time set by rotation. These ideas remain light and visual. The cone of emission rotates. It traces a circle in space. Most of the time that circle points elsewhere. For a short interval it crosses a particular direction, and the faint glow becomes noticeable. A physical detail appears as an edge. The beam is not a perfect cone with uniform brightness. It has a sharper inner core and a softer outer skirt. The core produces a clean pulse. The skirt produces a gentler rise and fall. The next understanding settles in. Pulse shape can reveal beam structure. A narrow core yields a brief peak. A wider skirt yields a longer shoulder. This is a small unlock that arrives calmly. It explains why pulses are not all identical, even when periods are stable. The analogy stays distinct and quiet. It resembles a distant fan of mist passing across a stationary slit in darkness. The mist does not increase. The slit does not move. The crossing alone creates a rhythm of brightening and dimming. The payoff lands softly. A pulse's regularity is a consequence of rotation paired with a narrow window of visibility. The main visual anchor deepens. The cone of glow passes behind the star and then returns. Near the surface field lines curve tightly. Farther out they open. The beam follows the open region like a corridor. Light behaves as if it prefers these open paths where particles can stream. The beam's boundary stays crisp near the core. It becomes fuzzier at the edges as scattering and spread increase. A second visual moment arrives to keep the cadence slow. A faint ring of emission forms farther out along open field lines. It is not a physical ring of matter. It is a region where conditions favour radiation. The ring looks like a thin halo segment suspended above the pole. As the star rotates, the segment sweeps around, painting a dim arc through space. The next understanding arrives as another unlock. Tilt is essential. If the magnetic axis aligned perfectly with rotation, the beam would not sweep across new directions. It would circle in place like a stationary cone. With tilt, the cone wobbles around the rotation axis. That wobble creates the sweep that produces pulses. The analogy remains distinct. It resembles a garden sprinkler head that is slightly angled. The water stream forms a rotating arc. Only directions inside the arc become wet. The payoff lands calmly. Pulses are a map of angles. They encode how rotation and magnetism are oriented. The section's single number appears and stays simple. A typical pulsar can pulse about once every second, like a steady drip of soundless light returning again and again. The comparison keeps it gentle and familiar. The scale shift follows softly. A single second becomes a repeated unit that can persist for millions of years. A short interval becomes a long-lived pattern. The visual anchor returns. The beam's inner core passes across the same direction each rotation. The rise is sharp. The fall is soft. The pulse feels like a brief brightening on an otherwise dark timeline, yet there is no timeline on display. Only the imagined rhythm exists in the empty region. The next understanding becomes clear. Pulsars can slow down over time. The pulse period lengthens as energy is lost through radiation and particle outflow. The change is gradual. The rhythm remains stable enough to measure. This unlock arrives quietly. A tiny drift in the beat carries information about how the magnetosphere sheds energy. A limit of observation appears and is stated plainly. The beam cannot be seen from all directions. If the beam never crosses a particular line of sight, the pulsar remains hidden even if it is active. This is a geometric selection effect. It limits which pulsars are detectable by their pulses. In addition, pulse shape depends on uncertain emission physics. Different beam models can reproduce similar pulse profiles. The limit is a limit of inference and of degeneracy in geometry. Without knowing the full three-dimensional orientation, multiple configurations can match the same pattern. The third visual moment arrives to keep the rhythm calm. The star turns beneath a quiet magnetospheric haze. Two polar regions glow faintly, one brighter than the other. The brighter one casts a narrow, sweeping cone. The dimmer one casts a broader, softer sweep. The boundaries of both beams remain subtle. The space around them stays dark and still. The final unlock settles gently. A pulsar is a rotating neutron star whose magnetosphere creates directional emission. The pulse is the moment the direction aligns. The section closes with a soft transition. Some pulsars are not smooth in their timing. Tiny jumps and jitters appear. The next step follows these timing irregularities and what they reveal about crust and interior coupling. A pulsar's steady rhythm sometimes shows a tiny stumble that quickly settles. The key idea is that the crust and interior do not always spin in perfect unison, so a sudden adjustment can slightly change the pulse rate. In that region, the neutron star remains small and dark. Its surface is a hard shell with subtle ridges and shallow basins. The main visual anchor settles on a close view of the crust as a brittle mosaic. Hairline fractures trace faint polygon patterns. Some shifts are too small to see directly, yet they matter. The first understanding arrives early. Timing irregularities can come from an internal coupling, not from changes in the beam alone. The pulse period is set by rotation. If rotation changes even a little, the timing shifts. The section keeps to three concepts. Crust is the rigid outer shell that can store stress. Superfluid is a frictionless liquid state in the interior. Glitch is a sudden small spin change seen in timing. The new term stays short and then returns to plain language. Superfluid is a liquid that flows without internal friction. The analogy stays distinct and quiet. It resembles a calm layer of oil that slides smoothly under a sheet of ice. The oil does not cling. It can move with its own pace. The payoff lands softly. If part of the interior slips relative to the crust-stored rotation can be transferred, and the surface rhythm can adjust. The visual anchor deepens. The crust looks like dark ceramic under immense gravity. It is not warm and it is not soft. It holds stress like a rigid plate. Beneath it, the interior is denser and stranger. A boundary exists between the rigid shell and the more fluid region. It is not perfectly sharp. It is a transition zone where vortices and pinning can occur. A physical detail appears as a pattern of lines. In the interior, rotation can be carried by tiny whirl structures. These whirl structures can anchor to irregularities near the crust. The next understanding arrives as a calm unlock. A glitch can occur when the interior and crust realign. The pulse rate jumps slightly, then continues. The change is small, yet it is measurable in principle through timing alone. The analogy remains gentle. It resembles a clockwork spring that is wound unevenly. When a catch releases, the spring gives a tiny extra turn and then returns to steady motion. The payoff lands softly. Glitches reveal that the star is not a single solid spinning as one piece. It is layered and coupled. The section's single number appears and stays safe. A typical glitch can change the spin by about 1 part in a million, like a metronome that gains a single beat after a long night of steady ticking. The comparison keeps it calm and avoids symbols. The scale shift follows gently. A change too small to notice in 1 second can accumulate into a clear offset over weeks and months. Small differences become visible only through patience and long baselines. The second visual moment arrives as a slow checkpoint. A faint band on the crust shifts by a fraction of its width. The band is imagined as a brightness gradient caused by temperature differences or composition. The gradient is not dramatic. It simply marks the crust as structured rather than smooth. The shift is subtle, yet in timing, subtle becomes real. The next understanding settles in. The interior superfluid can store angular momentum differently than the crust. When vortices pin and unpin, transfer can occur in steps rather than in a continuous drift. The concept stays plain. Rotation is shared through coupling. Coupling is not always perfect. The payoff arrives as another unlock. A glitch is a probe of the interior's state. It hints at how matter behaves under extreme density. The main visual anchor returns. The brittle mosaic is seen again now with a thin line that lengthens. The line is a fracture or a slip plane. It does not open into a gap. It is more like a rearrangement of stresses. The shell stays intact. It simply shifts to a slightly different equilibrium. A third visual moment arrives to keep the cadence steady. Deep beneath the crust, a dark interior holds quiet motion. Tiny whirl structures form a sparse lattice. They drift, then pause, then drift again. The motion is almost still when seen from far away, yet it carries the star's rotational history. The next understanding becomes clear. Not all timing irregularities are glitches. Some are timing noise slow wander in the pulse arrival times. This can come from magnetospheric changes. It can also come from complex coupling inside. The section stays focused on the internal story. The limit of observation appears and is stated plainly. The crust and interior cannot be seen directly. Only pulse timing and broad emission properties offer clues. Many different internal models can reproduce similar glitch patterns. The limit is a limit of inference and of model degeneracy. Even when a glitch is measured precisely, the path from timing to interior physics is not unique. Uncertainty remains as a set of plausible mechanisms rather than a single answer. The payoff lands softly. Even without direct access, timing provides a way to sense layers that are otherwise hidden. A gentle scale shift closes the section. A fracture line measured in centimeters on the crust can influence a timing record that spans years. A tiny internal rearrangement can echo as a persistent offset in a distant rhythm. The section ends with a calm transition. Beyond glitches, some neutron stars show much stronger magnetic stress and different kinds of irregular behavior. The next step follows those extreme magnetic cases and how they reshape the crust and magnetosphere. A magnetar appears calm from afar, yet its space is shaped by unusually intense magnetic order. The key idea is that an extreme magnetic field can stress the crust and twist the magnetosphere, changing how energy is stored and released. In that region, the neutron star is still a small dark sphere. Above it, the magnetosphere looks thicker and more structured than before. The main visual anchor settles on a set of twisted arcs, rising from the surface like braided ribbons of faint glow. The braids do not shine brightly. They are traced by a thin veil of particles that follows the curvature. The first understanding arrives early. A magnetar is a neutron star where magnetism dominates the story. Rotation still matters, yet the magnetic environment becomes the main driver of behavior. The section keeps to three concepts. Magnetar is a neutron star with an exceptionally strong magnetic field. Magnetic stress is force stored in field geometry and crustal strain. Twisted magnetosphere is a field structure that departs from a simple dipole shape. The new term stays short and then returns to plain language. A magnetar is a neutron star with an unusually strong magnetic field. The analogy stays distinct and quiet. It resembles a tightly wound spring hidden inside a smooth object. The object looks still. The spring holds tension in its shape. The payoff lands softly. When magnetic structure is tight and twisted, energy can be stored in geometry, rather than in motion or heat. The main visual anchor deepens. The braided arcs lean and curve back toward the surface. Their curvature is sharper near the star. Farther out, the arcs widen and relax. A physical detail appears as a boundary. There is a region where the twist is concentrated. Inside it, field lines are crowded. Outside it, the geometry becomes simpler and more open. The boundary is not a wall. It is a steep gradient in field direction and particle density. A second visual moment arrives to keep the cadence even. Two oval patches near the magnetic poles glow faintly. The patches are not smooth. They have mottled brightness as if the surface temperature varies in small islands. The edges of the patches are sharp. The interior brightness fades toward the center. The next understanding settles in. Magnetic stress can couple to the crust. The crust is rigid. It resists deformation, yet it can store strain. When magnetic structure changes slowly, the crust can be pulled and sheared. When strain grows too large, the crust can shift. The shift can be small, yet it changes the magnetosphere. The payoff arrives as a gentle unlock. Magnetars are not defined by what is seen in a single moment. They are defined by how field and crust interact over time. The section's single number appears and stays safe. A magnetar's magnetic field can reach about 1,000 trillion times the strength of Earth's field, like turning a simple compass into a useless idea at any distance nearby. The comparison stays every day without invoking tools in the scene. It frames the scale without showing any human object. The meaning is clear. Ordinary magnetic intuition breaks down. The scale shift follows softly. A field that is gentle across an entire planet becomes overwhelming within a region only a few star radii across. A small neighborhood in space becomes a dominant landscape. The main visual anchor returns as the braided arcs tighten. The arcs twist around an invisible axis. The twist is not decorative. It changes how particles move and where they can radiate. Light behaves as if emission prefers the twisted corridors. Some paths brighten, others dim. A third visual moment arrives to keep the rhythm calm. A thin sheet of particles hangs above an equatorial region like a soft curtain. The curtain is not uniform. It has ripples and folds that align with field curvature. Along the folds, the glow is slightly stronger. The next understanding becomes clear. Twists in the magnetosphere can increase electrical currents in space. Those currents can heat regions and alter emission. The process can be gradual. It can also reorganize quickly when geometry shifts. This is stated without sharp drama. The payoff lands softly. A changing field can change the signal without requiring changes in rotation. A limit of observation appears and is stated plainly. The internal magnetic field cannot be mapped directly. Only surface emission timing and broad spectral changes provide clues. Different internal field configurations can produce similar external behavior. The limit is a limit of inference and of model ambiguity. Surface hotspots can shift for multiple reasons. Magnetospheric twists can be arranged in several geometries that look alike from far away. Uncertainty remains as a family of possibilities rather than a single blueprint. The visual anchor returns with a slow concrete pass. The braided arcs loosen slightly. The oval polar patches fade, then brighten again. The crust remains a dark shell beneath it all. Fine fracture lines are suggested along the surface, faint and shallow. They do not gape open. They mark where strain prefers to collect. The payoff settles in as a final clarification. Magnetars show that magnetic fields can be a primary engine in a neutron star's life. They shape space-stress the crust and organize emission through geometry. The section ends with a gentle transition. The next step follows deeper structure inside the star where nuclei can form unusual shapes under immense pressure. The journey moves inward from magnetosphere and crust toward the strange architectures of compressed matter. Deep inside, a neutron star matter can arrange itself into shapes that feel more like geometry than substance. The key idea is that extreme pressure can force nuclei into rods and sheets, creating layered structures sometimes called nuclear pasta. In that region, the star's interior is not seen directly. It is imagined as a sequence of zones where density and composition change with depth. The main visual anchor settles on a cutaway view of the inner crust. A dim layered landscape appears. Long parallel ridges run through it like slow waves frozen into stone. Between ridges, narrow channels form darker valleys. The first understanding arrives early. At sufficiently high density, nuclei stop being tidy spheres. Competing forces push them into extended shapes. Gravity provides the overall squeeze. Nuclear attraction pulls matter together at short range. Electric repulsion resists crowding of protons. The balance between these forces can favour shapes that spread out rather than clump. The section keeps to three concepts. Nuclear pasta is dense matter forming rod and sheet like nuclear shapes. Inner crust is the region beneath the solid outer crust where nuclei coexist with free neutrons. Competing forces is the push and pull between nuclear attraction and electric repulsion. The new term stays short and then returns to plain language. Nuclear pasta is dense nuclear matter shaped into rods and sheets. The analogy stays distinct and quiet. It resembles dough pressed through a flat grate. The dough does not become different dough. It becomes strands and layers because the pressure forces it into paths. The payoff lands softly. Shape is a response to constraint. Under extreme compression, matter chooses forms that reduce energy in a crowded environment. The main visual anchor deepens. The inner crust looks like a layered maze. Some regions resemble long tubes packed side by side. Some resemble thin plates stacked with narrow gaps. The physical detail is the presence of repeated boundaries. Each plate has an edge. Each tube has a wall. Between them, free neutrons move like a background fluid. The contrast between solid-like structures and mobile neutrons becomes a gentle theme. A second visual moment arrives to keep the cadence even. A slow gradient of density appears from one layer to the next. The ridges are thicker deeper down. The channels become narrower. The pattern changes smoothly, then reorganizes into a new pattern. The next understanding settles in. The inner crust is not uniform. It transitions through different arrangements as pressure increases. Spherical nuclei can become elongated. Elongated nuclei can merge into sheets. Sheets can break into voids. The changes occur because the system seeks the lowest energy structure available at that density. The payoff arrives as a calm unlock. The interior can behave like a material with faces where structure changes without changing ingredients. The section's single number appears and stays safe. The thickness of the crust can be about 1 kilometre, like the height of a large mountain spread as a shell around a city-sized sphere. The comparison holds scale gently. The shell is thin compared with the star, yet it contains complex structure. The scale shift follows softly. Within that kilometre, microscopic interactions determine macroscopic stiffness. Tiny forces between particles shape how the star responds to stress and spin. The main visual anchor returns as the layered maze seems to flex. It does not bend like rubber. It deforms in small rearrangements. The boundaries between plates and channels guide where strain can accumulate. This links back to earlier themes without repeating them. A third visual moment arrives calm and concrete. In a darker layer, a pattern looks like stacked pages pressed together. The pages are not paper. They are dense nuclear sheets. The gaps between them are narrow corridors where neutrons move more freely. Light behaves as if it cannot penetrate this scene. It is an interior vision only. The next understanding becomes clear. These structures matter because they affect how the crust conducts heat and how it resists shear. They can influence how stress builds and releases. They can also influence how the star's rotation couples to its interior through pinning of rotational structures in the neutron fluid. The payoff lands softly. A strange geometry can leave fingerprints on timing and cooling, even when it cannot be seen. A limit of observation appears and is stated plainly. Nuclear pasta cannot be observed directly inside a neutron star. Its existence is inferred from theoretical models and from how crust properties affect measurable signals like cooling trends and timing behavior. Many different microphysical assumptions can produce similar macroscopic outcomes. The limit is a limit of inference and of model uncertainty. Even if the star's mass and radius are known, multiple cross models can fit. That boundary does not erase the concept. It keeps it humble and plausible rather than absolute. The main visual anchor returns for a final slow pass. The ridges and sheets fade into deeper darkness. The pattern becomes less like a maze and more like a continuous medium. The inner crust gives way to the core where matter may become more uniform again. The payoff settles in as a final clarification. Nuclear pasta is an example of how structure emerges under constraint. It shows that extreme environments do not destroy order, they replace familiar order with new geometry. The section closes with a gentle transition. Beneath these layers, the core remains more uncertain. The next step follows what might exist at the deepest densities, and why that uncertainty persists even with careful signals. The deepest interior of a neutron star is quiet, yet it holds the largest uncertainty in the story. The key idea is that several different core states can fit the same outward measurements, so the center remains a range of possibilities. In that region, a cutaway view shows the star as nested layers fading into a darker core. The main visual anchor settles on a smooth gradient sphere within the sphere. The outer layers show texture and structure. The inner region looks like a dim fog that thickens toward the center. The first understanding arrives early. The core is not a place where certainty ends. It is a place where evidence becomes indirect. The star's mass and radius constrain what can exist. The details still branch into multiple options. The section keeps to three concepts. Equation of state is how pressure relates to density inside matter. Phase transition is a change of matter state under new conditions. Maximum mass is the largest stable mass a neutron star can hold. The new term stays short and then returns to plain language. Equation of state is the rule linking pressure and density. The analogy stays distinct and quiet. It resembles a recipe that tells how thick batter becomes as flour is added. The batter is the same ingredients. The thickness follows a rule. The payoff lands softly. If the rule is known, the star's size and stability become predictable. If the rule is uncertain, several interiors remain plausible. The main visual anchor deepens. The core's gradient grows steeper with depth. There are no visible walls, yet imagined boundaries appear where matter might reorganize. One boundary could mark a shift from ordinary neutrons to a more exotic mixture. Another could mark a smoother change without a sharp transition. The physical detail is the presence of layering as a possibility. Even when a boundary is uncertain, the idea of a boundary matters because it changes how sound and heat travel. A second visual moment arrives to keep the cadence even. A faint ripple passes through the interior in imagination. The ripple slows where matter is stiffer. It speeds where matter is softer. The next understanding settles in. Different equations of state produce different stiffness. Stiffer matter resists compression more. Softer matter compresses more under the same gravity. This changes the radius for a given mass. It also changes the maximum mass before collapse. The payoff arrives as a calm unlock. The core's microphysics controls a macroscopic property that can in principle be measured from far away. The section's single number appears and stays safe. The maximum mass is thought to be around 2 solar masses, like a star's worth of weight balanced on a sphere about the size of a city. The comparison keeps the scale grounded. It also ties stability to a limit. If a neutron star exceeds this range, collapse becomes likely. The scale shift follows softly. Particle interactions at distances smaller than atoms decide whether an object survives for billions of years. Tiny rules govern long outcomes. The main visual anchor returns. The fog-like center thickens. A sense of depth increases. The core becomes a place where language becomes cautious. A phase transition is introduced gently. Phase transition is a change in matter's form under new conditions. The analogy stays distinct and calm. It resembles water turning to ice when temperature crosses a threshold. The ingredients stay the same. The structure changes. The payoff lands softly. If a transition occurs in the core, it can change stiffness and alter the star's radius and oscillations. The section does not chase a catalogue of exotic states. It keeps one idea present. At extreme density, matter may shift from neutrons to components that are normally confined inside them, or it may remain mostly neutrons with subtle additions. The point is not to pick a winner. The point is to see why multiple interiors remain viable. A third visual moment arrives to hold the rhythm. A smooth spherical boundary is imagined within the core, barely distinguishable from the surrounding gradient. On one side, the interior responds more stiffly to compression. On the other, it yields slightly more. The boundary is not a crack. It is a change in how pressure grows with density. Light behaves as if it cannot report this change. Only gravity and timing can hint. The next understanding becomes clear. Observations use outward signals to infer inward rules. Mass can be measured in binary systems through orbital effects. Radius can be inferred through thermal emission and lensing. Tidal effects during close interactions can also constrain stiffness. Yet each path has uncertainty. The limit of observation appears and is stated plainly. The core cannot be directly sampled. Radius estimates depend on models of surface emission and atmosphere. Mass estimates depend on orbital interpretation. Tidal constraints depend on complex modelling. The limit is a limit of inference and of degeneracy among models. Different equations of state can fit the same set of measurements within error bars. This keeps the core uncertain even when the star is well studied. The payoff lands softly. Uncertainty is not ignorance. It is a narrowing corridor of possibilities guided by multiple clues. The main visual anchor returns for a final slow pass. The fog-like centre remains dim and smooth. The outer layers remain structured and clearer. The star holds its secret without hiding its influence. The section closes with a gentle transition. Some of the best new constraints come when neutron stars interact in pairs and their orbits tighten. The next step follows that slow spiral and how it carries information outward through space. Two neutron stars can circle each other so slowly that the change is almost imperceptible at first. The key idea is that the orbit tightens because energy is carried away by gravitational waves, so the pair spirals inward over time. In that region, space looks empty and calm. Two compact spheres move along a shared path. The main visual anchor settles on their orbital plane as a thin, pale ellipse traced in darkness. The ellipse is not a physical line. It is a faint imprint suggested by a slight density of drifting dust that is gently stirred by gravity. The first understanding arrives early. Gravitational waves are not light and not sound. They are ripples in space-time that carry energy away from accelerating masses. When the pair orbits, each star accelerates continuously. That acceleration produces ripples that spread outward. The section keeps to three concepts. Gravitational waves are travelling ripples in space-time curvature. Inspiral is the gradual shrinking of an orbit over time. Tidal deformation is the stretching of each star by the other's gravity. The new term stays short and then returns to plain language. Gravitational waves are ripples in space-time that travel outward. The analogy stays distinct and quiet. It resembles a slow pulse travelling across a calm pond. The pond surface is not carried away. The pattern moves outward and energy moves with it. The payoff lands softly. Energy can leave the system without any material being thrown out, and the orbit responds by tightening. The main visual anchor deepens. The elliptical path slowly rounds into a tighter curve. The separation decreases. The stars remain dark and compact. Around them the dust haze is sparse. It traces their motion only faintly. A physical detail appears as a gradient in spacing. The orbit is widest at one point and narrowest at another. Over many cycles, the entire ellipse shrinks. The narrowest point becomes narrower. The widest point becomes less wide. The next understanding settles in. Inspiral is not a sudden plunge from the beginning. It begins as a slow drift. Each orbit loses a tiny fraction of energy. The period shortens a little. The stars complete cycles slightly faster. This unlock arrives quietly. A long story can be encoded in small changes. Tiny losses per orbit accumulate into a strong late-stage acceleration. The analogy remains calm and distinct. It resembles a leaf sliding down a shallow bowl. At first the leaf barely moves. As it reaches a steeper region, the slide becomes more obvious. The payoff lands softly. The inspiral accelerates naturally because gravity grows stronger as distance shrinks, and stronger acceleration produces stronger ripples. A second visual moment arrives to keep the cadence even. The two spheres draw closer. Their paths become nearly circular. The surrounding space shows a faint pattern of alternating compression and stretching. The pattern is not visible light. It is imagined as subtle distortion of the dust haze, a gentle breathing of geometry. Light behaves as if it remains indifferent to these ripples. The ripples pass through without scattering light in the usual way. The section's single number appears and stays grounded. In the final minutes, the orbital frequency can reach hundreds of cycles per second, like a humming vibration far above a slow heartbeat. The comparison keeps it familiar without invoking any person. The scale shift follows softly. A process that begins over millions or billions of years can end in minutes. A slow drift becomes a rapid sweep. The main visual anchor returns. The ellipse has now become a tight circle. The stars are close enough that their gravity begins to stretch each other. The stretching is not a tear. It is a subtle distortion. A physical detail appears as an elongation along the line between the stars. Each star becomes slightly egg-shaped. The long axis points toward the companion. The next understanding becomes clear. Tidal deformation depends on how stiff the star is. A stiffer star resists stretching more. A softer star stretches more. This affects the phase of the gravitational wave signal near the end. The payoff lands softly. The waveform is not just a clock of orbital motion, it is also a probe of the star's internal rule linking pressure and density. The section does not require a diagram. The idea is held in words. The stronger the tide, the more the orbit and signal deviate from two perfect point masses. The deviation is subtle, yet subtle changes in the latent spiral can constrain the equation of state. A third visual moment arrives to maintain the gentle rhythm. A faint bulge on each star's near side rises and falls as the orbit tightens. The bulge is small, its outline is smooth. A shallow gradient of curvature appears across the surface, slightly steeper near the facing sides. The motion is quiet, like a slow breathing of shape. The limit of observation appears and is stated plainly. Gravitational waves measure a combination of masses, spins, and tidal properties. These parameters can trade off in the models that interpret the signal. The same observed pattern can sometimes be matched by different combinations within uncertainty. The limit is a limit of inference and of parameter degeneracy. In addition, the exact contribution of spin and eccentricity can be difficult to separate from tides without very high signal quality. That boundary does not erase the method. It sets expectations for ranges rather than exact interior maps. The payoff arrives softly. Even with uncertainty, in spiral signals shrink the space of possible interiors more than isolated stars often can. The main visual anchor returns for a final slow pass. The two spheres are now very close. The orbit is tight and fast. The dust haze is disturbed into a faint spiral pattern that trails behind then fades. The spiral is not awake in a fluid. It is a visual stand-in for changing gravitational geometry. The section closes with a gentle transition. After the final tight orbit, the system changes quickly. The merger forms a brief complex remnant and then settles toward a new state. The next step follows that post-merger evolution, and what remains as the waves and light fade. After a neutron star merger, the remnant exists as a brief balance between collapse and support. The key idea is that rotation pressure and heat can temporarily hold up a massive remnant, and then the system settles into a more stable state. In that region, the scene begins as a tight, bright knot of matter and field. It is not a smooth sphere. It is a distorted, rapidly changing shape with a thick equatorial bulge. The main visual anchor settles on a spinning oblate remnant surrounded by a thin, expanding cloud. The cloud forms a faint spiral shell that widens outward, then thins into darkness. The first understanding arrives early. The merger does not immediately become a quiet object. It becomes a remnant with intense motion and strong gradients. Density is highest near the center. Temperature and composition vary with radius. The section keeps to three concepts. Remnant is the merged object formed right after coalescence. Differential rotation is when different layers spin at different rates. Ejecta is material that escapes the central remnant. The new term stays short and then returns to plain language. Differential rotation is layers spinning at different speeds. The analogy stays distinct and calm. It resembles a river with faster flow in the middle and slower flow near the banks. The water is one river. The speed varies across it. The payoff lands softly. When spin varies by layer, extra support against gravity can exist for a short time. The main visual anchor deepens. The remnant surface is not smooth. It shows a thickened waist and shallow lobes that rise and fall. A physical detail appears as a boundary. The equatorial bulge has a sharper edge where density drops rapidly. Above and below the equator, the surface curves inward more steeply. Around the remnant, the cloud is not uniform. It is denser in an equatorial band and thinner toward the poles. A second visual moment arrives to keep the cadence even. The expanding cloud forms a faint shell with a layered texture. The inner layer is slightly brighter. The outer layer is more diffuse. Between them, a soft gradient appears, suggesting changing speeds within the outflow. The next understanding settles in. Ejecta carries away mass and angular momentum. This can help the remnant stabilize. It can also reduce the mass left behind, nudging the system away from immediate collapse. The payoff arrives as a calm unlock. The fate of the remnant depends on small differences in mass and rotation, not only on the violence of the merger. The section's single number appears and stays grounded. The fastest ejecta can move at about 1/3 the speed of light, like a wavefront that crosses the distance from Earth to the Moon in a little over a second. The comparison is familiar without placing any human presence in the scene. The scale shift follows softly. An outflow that begins in milliseconds can expand into a cloud spanning millions of kilometers within hours. A brief moment becomes a vast, thinning shell. The main visual anchor returns as the oblate remnant spins. Differential rotation slowly reduces as internal forces redistribute angular momentum. Heat also escapes. As the remnant cools, pressure support changes. The shape becomes less lopsided. The bulge remains, yet it steadies. The next understanding becomes clear. There are several possible endpoints. The remnant can become a stable neutron star if mass is low enough. It can collapse into a black hole if mass is too high. It can also remain temporarily supported, then collapse, after losing rotational support. This is stated gently without suspense. The payoff lands softly. The post-merger stage is a gatekeeper. It determines what kind of compact object remains and what signals persist. A third visual moment arrives slow and concrete. The surrounding cloud shows faint clumps and filaments. The filaments trace gentle arcs as they drift outward. A darker cavity opens near the poles where less material escapes. The physical detail is the layered edge of the cloud. The edge is not sharp. It is a fading gradient where particles become too sparse to matter. Light behaves as if emission from the cloud depends on composition and temperature, not on a single uniform glow. The limit of observation appears and is stated plainly. The remnant's internal state cannot be directly measured. Late-time signals from the cloud depend on uncertain microphysics, including how heavy elements form and how radiation escapes from an expanding mixture. The limit is a limit of modelling, and of incomplete knowledge of opacities and heating rates. Different assumptions can produce similar brightness curves. In addition, gravitational wave signals after merger can be weak and short, making precise interpretation difficult. The payoff arrives softly. Even with these limits, the presence or absence of long-lived remnant signatures can constrain the equation of state and maximum mass. The main visual anchor returns for a final slow pass. The oblate remnant dims in imagination as it cools. The spiral shell continues outward. Its inner edge smooths. Its outer edge dissolves into the background. The scene becomes quieter. The system transitions from rapid change to slow evolution. A gentle scale shift closes the section. The merger's central drama lasts seconds. The resulting object and its debris can influence the surrounding space for thousands of years as the cloud expands and fades. The section ends with a calm transition. After the merger story, another signal remains steady in many neutron stars. Cooling light carries information about layers and composition. The next step follows how neutron stars lose heat, and what that cooling reveals. A neutron star cools in silence, and that slow fading can reveal what lies beneath the surface. The key idea is that heat leaves through neutrinos from the interior and through photons from the surface, and the balance changes with age. In that region, the scene begins with a lone neutron star drifting through darkness. The main visual anchor settles on its surface as a faint, even glow. The glow is not bright. It is a soft sheen that follows the curvature like moonlight on smooth rock. The surface is not perfectly uniform. A gentle gradient runs from one hemisphere to the other. The first understanding arrives early. Cooling is a timeline written in temperature. Early on, the interior sheds energy mainly through neutrinos. Later, the surface glow becomes a larger fraction of what escapes. This is not a story of visible fire. It is a story of hidden channels that carry energy away. The section keeps to three concepts. Neutrino cooling is heat loss through weakly interacting particles from the interior. Thermal conductivity is how easily heat flows through the crust and core. Superfluidity is a low friction state of neutrons in the interior. The new term stays short and then returns to plain language. Neutrino cooling is heat carried away by neutrinos from inside. The analogy stays distinct and calm. It resembles a fog that carries warmth away without leaving a trace. The air does not glow, the warmth simply departs. The payoff lands softly. A star can cool rapidly even when little light is seen because much energy leaves in invisible form. The main visual anchor deepens. The surface glow dims slowly. The gradient across the surface becomes more structured. A faint band appears around mid-latitudes. The band is slightly warmer than adjacent regions. A physical detail appears as a boundary in temperature. The band has a soft edge that blends outward. Near the poles, the glow is faintly different in tone. The surface pattern is guided by the star's magnetic field, which channels heat flow in the crust. A second visual moment arrives to keep the cadence even. A cutaway view returns. The crust appears as a thin shell with layered texture. Beneath it, the interior looks smoother. Heat flows upward like a slow seep through porous stone. The seep is not liquid. It is an image for diffusion through dense matter. The next understanding settles in. Thermal conductivity controls how quickly interior heat reaches the surface. If conductivity is high, the surface follows the interior more closely. If conductivity is lower, the crust can act like an insulating layer. The payoff arrives as a calm unlock. Surface temperature is not only a measure of how much heat exists, it is also a measure of how easily heat can travel outward. The section's single number appears and stays safe. In the first 1,000 years, a neutron star can cool from tens of millions of degrees to a few million degrees, like a kiln that loses its fiercest heat and settles into a steady warmth. The comparison keeps the idea grounded without invoking any human presence in the scene. The scale shift follows softly. A change that seems slow on a night sky can be fast on cosmic timescales. A few thousand years is a blink compared with the star's potential lifetime. The main visual anchor returns. The surface glow continues to fade. The banded pattern shifts subtly. The cooler regions expand. The warmer regions shrink. The next understanding becomes clear. Superfluidity can alter cooling. Superfluidity is a low-friction neutron state in dense matter. The analogy stays distinct and quiet. It resembles a crowd moving through a hallway without jostling where motion meets little resistance. The payoff lands softly. When neutrons become superfluid, heat capacity changes and certain neutrino emission processes can switch on or off. This can create changes in the cooling curve. The section remains gentle and avoids technical clutter. The important point is that microphysics shapes the slope of temperature over time. The crust composition also matters. If the crust contains impurities, heat flow can be hindered. If it is purer, heat can move more freely. The surface pattern can also reflect magnetic geometry, since heat prefers to travel along field lines more than across them. A third visual moment arrives slow and concrete. The star's surface shows a soft mottling, like faint islands of warmth within a cooler sea. The edges of the islands are not sharp. They fade through a gentle gradient. The islands drift in place over time in the imagination not by motion, but by changing relative brightness as the interior cools. Light behaves as if it carries only the final step of the heat's journey. Most of the story happens deeper down. The limit of observation appears and is stated plainly. Cooling curves are inferred from surface emission and distance estimates. Surface emission depends on the thin atmosphere and magnetic field, which shape the spectrum and apparent temperature. Different atmosphere compositions can mimic different temperatures. Distance uncertainties can shift inferred luminosities. The limit is a limit of model dependence and of indirect inference. Even when a temperature is measured, translating it into interior conditions requires assumptions about conductivity, superfluid gaps and composition. That boundary does not erase the method. It encourages comparing many stars across ages to find patterns rather than trusting any single object. The payoff arrives softly. A population of cooling curves can narrow interior possibilities because the same model must fit many timelines at once. The main visual anchor returns for a final slow pass. The faint surface glow becomes more uniform as overall temperature falls. The banded pattern becomes subtle. The star looks calmer. The cooling continues for millions of years. Eventually, the surface emission becomes very faint against space. Another gentle scale shift closes the section. Microphysical changes in the first few thousand years can echo into the star's long future, shaping how quickly it approaches equilibrium with its surroundings. The section ends with a calm transition. After signals of timing, magnetism, merger waves, and cooling light, the story can step back and gather the lessons into a single quiet perspective. The next step moves toward that wide view and a soft landing. Across the quiet distance, a neutron star can be understood as a compact archive, where nature writes in density, rhythm, and fading heat. The central truth is that signals from spin gravity and cooling connect back to layered matter under extreme pressure. In that region, the scene opens with a wide field of darkness. A sparse mist of dust drifts in slow sheets. Near the center of the frame, a neutron star appears as a small dim bead. The main visual anchor settles on the star's silhouette against a faint background glow. Around the silhouette, a thin, pale halo forms a soft ring. The ring is not a physical disk. It is a gentle lensing imprint, a subtle brightening where light bends around the compact mass. The first understanding arrives early. Many lessons come from changes, not from images. A pulse can mark rotation. A chirp can mark an inspiral. A fading glow can mark cooling. Each is a different path to the same interior. The section keeps to three concepts. Equation of state is the rule linking pressure and density in dense matter. Signal is an observable pattern in time that carries physical information. Degeneracy is when different models produce similar signals. The new term stays short and then returns to plain language. Equation of state is the rule connecting pressure and density. The analogy stays distinct and calm. It resembles a recipe that determines how a batter thickens as more flour is added. The ingredients are the same. The texture depends on the rule. The payoff lands softly. When the rule is known, mass and radius become connected and many signals gain a clear interpretation. The main visual anchor deepens. The silhouette remains crisp. The halo ring remains faint. A physical detail appears as a sharp limb. The edge of the star is a hard boundary for ordinary matter. Just above it, space remains clear. Light behaves as if it curves gently near the limb. The ring brightens slightly on one side, then dims. The variation is not a flicker. It is a slow shift in viewing geometry, a calm movement of the background glow through curved paths. A second visual moment arrives to keep the cadence even. The scene pulls closer in imagination without any sudden motion. The surface becomes a smooth arc. A thin, cooler band lies near the equator. It is visible only as a faint gradient in brightness. The band fades into darker regions toward higher latitudes. The next understanding settles in. Different signals sample different depths. A pulse from a hotspot traces surface conditions and magnetic geometry. A gravitational wave chirp traces mass compactness and tidal response. Cooling traces conductivity and interior particle states. The payoff arrives as a calm unlock. No single signal tells the full story, yet together they constrain what is possible. The section's single number appears and stays grounded. The star's radius is about 12 kilometers, like a city-sized circle compressed into a sphere. The comparison keeps scale familiar without introducing any human presence in the scene. The scale shift follows softly. A region only tens of kilometers across can influence waves that travel for millions of years through space. A tiny object can set a rhythm that remains readable across the galaxy. The main visual anchor returns. The halo ring remains thin and quiet. The background glow stays diffuse. The star's limb remains sharp. The next understanding becomes clear. Degeneracy is always a companion to inference. A signal can be matched by more than one combination of mass, spin, and interior properties. The limit of observation appears and is stated plainly. Many measurements are indirect. Distance estimates can be uncertain. Atmosphere composition can shift inferred temperatures. Magnetic geometry can mask true surface patterns. In gravitational waves, parameter correlations can hide unique solutions. The limit is a limit of model ambiguity, an incomplete priors, not a failure of the signals themselves. The payoff arrives softly. Limits guide careful comparisons across many sources. Consistency across different kinds of data narrows the interior rule more than any single channel can. A third visual moment arrives slow and concrete. The halo ring seems to widen then thin as the imagined viewpoint drifts. Behind it, the dust mist forms faint striations. The striations bend slightly near the star, then straighten far away. The physical detail is the curvature gradient. Close to the limb bending is stronger. Farther out it fades smoothly. The scene remains calm. The story does not need explosions. It rests on patterns that change gently, and on boundaries that are sharp but quiet. The section gathers the arc without labels. The dense core sets a rule. Rotation turns that rule into timing. Tides reveal stiffness through orbital changes. Cooling reveals pathways for heat. Merger remnants show how close matter comes to collapse, and how support can persist briefly. Each checkpoint returns to the same theme. Extreme density is not only a condition, it is a test of physical laws. The closing scale shift settles into a soft landing. The star cools over millions of years. Its pulses can persist for longer. The halo ring can remain as long as light passes nearby. In the wider view, the object becomes one small point among many. Yet it continues to encode a deep interior in gentle, measurable patterns. The scene eases back into darkness. The halo fades into the background glow. The dust mist drifts on. The final calm is not empty. It is structured by gravity rhythm and slow change.